In this video we will consider technology for manufacturing parts using rotocasting, and then we will try to reinforce them with composite materials. Likes and comments below, and let's begin!
What's up, Ironman fans? This is the video you've been waiting for so long. As you know, I continue to make my composite suit working on the hydrogen power system and composite external armor. Today I want to show you a new and rather complicated method for manufacturing body parts. I think you like it. We will print the master model on a 3D printer, fabricate a casting mold based on this model, make several plastic helmets, and if it works, we will try to reinforce some parts with fiberglass, carbon fiber or Kevlar to get body parts even lighter and stronger than we have achieved before. I know there will be thousands of different questions below this video, so if you have specific technical question based on the material from this video, please start your comment with the tech question. This will help me to find and answer your technical questions first. Let's go! In previous videos on composite materials, we have looked at several ways on how using 3D printing and multi-layer composite reinforcement make such prints that they are continued to look like original 3D models, but at the same time they are much stronger than simple 3D prints. The only thing I didn't like about this method was PLA plastic in the final part. In the 3D printing process, PLA is a perfect material. It doesn't smell or emit harmful substances during printing. PLA parts can be made on cheaper printers without a thermal chamber. It has ideal interlayer adhesion and minimal shrinkage, and you can print them even on cold table. According to these facts, PLA printing is much more simpler and cheaper than with other materials, and even if your small workshop is running 6 printers with PLA, this doesn't stop you from working at the same time. The nuances with PLA begin after 3D printing. If the printed parts need to be smooth and prepared for painting, then the PLA plastic itself very stubbornly processed with abrasive and quite unpredictably treated with chemicals. Therefore, for high-quality smoothing it is necessary to use much of quite expensive filler or primer and multi-day manual processing with abrasives. What makes 3D printing processing more expensive than 3D printing itself, but that is still not the main problem. The main problem with PLA parts, this is very low heat resistance. Softening of the plastic occurs at only 50 degrees, therefore parts can easily float in the strong sunlight or if you just left it in a car in a warm day. Composite reinforcement will certainly not allow them to completely lose their shape, but the coating will definitely be damaged. Therefore, if the body parts still contains PLA, this greatly narrows the sphere of application of such parts. In short, when you put in so much effort in 3D modeling, production and manual processing of the part, you don't want to worry about that they will simply melt into the sun on a hot day. If the problem is in PLA itself, it would be logical to replace it on ABS, filaments with carbon fiber or another heat-resistant material. And here we come to the classic material and tool contradiction. The more durable the material we use, the more difficult and expensive it is to process. In our case, for 3D printing with more heat-resistant materials, more expensive printers with thermal camera are needed, filaments are also more expensive, high-temp 3D printing itself is more expensive, and probably you won't be able to hang around in the garage during such printing. So I came to another option which would allow continued use all advantages of printing with PLA plastic, but avoid its use from the final part. So this is the plan. We still use PLA plastic, 3D print a master model of the required part, then we make a soft silicone mold on the top of this and rigid fiberglass shell. Then we can use this mold to make as many castings as we wish, and if the strength of the plastic is not sufficient, then we reinforce the casting from the inside with composite materials. Polyurethane plastic has higher heat resistance than PLA, and it's remarkably easy to process with abrasives even to a mirror shine, and with such body parts I would probably be satisfied. So, sit back and relax, make some tea, and now we dive into the nuances of this promising technology.
So, first we need to get a master model. During printing and all after processing, We are trying to get the highest quality of surface and detail which only printers and our hands are capable of. Because if everything works out, then according to this master model, we can make as many helmets as we like, but they will all copy every scratch of the original model. After printing large parts, there are usually small remains of PLA left on the spool, which are quite inconvenient to use for the next prints. If such waste also pains your economical soul, here's a little life hack for you. Take a soldering iron and craft a special nozzle for it. I used a brass rod, a lathe and a drilling machine for this, but the same kind of nozzle can be made from a large bolt using just a screwdriver or drill. Drill a hole at the end of the soldering iron tip and just below drill a hole for the Teflon tube from the extruder. Such spare tubes are always included with a 3D printer. The result is a convenient device for welding filament, allowing you to combine a bunch of small leftovers from different spools into one full-fledged spool. When the printer finishes its work, we begin processing our master model. Remove the supports and flash the part with a propane torch to quickly get rid of stringing and other minor print defects. If we want certain small details such as grooves, slots and small holes to be more visible on the final castings, it's better to accentuate these details additionally with a soldering iron. If the lines aren't deep enough, they can easily be filled with primer on the next smoothing stage and will simply disappear on the final part. Also, at this stage you can very carefully smooth out the roughest print defects with methylene chloride. But it's still better to manage without it, or if you use it, only a tiny amount. If you overdo it slightly, methylene chloride can easily dissolve the part deeper than intended, and such an area will then have to be built up for a long time with filler and primer. When you are constantly handling already printed part during processing, ideas often come to mind on how this part could have been modified to make it more convenient or look cooler. And that is completely normal, so don't be afraid to make changes where you need it, even after the part has already been printed. For example, during the processing stage, I understood that it would be convenient to place the faceplate opening buttons and the ventilation switch right into the ear slots. I found suitable buttons, but they turned out to be slightly larger in diameter than the slots, so I modeled new ear inserts, cut out the old ones and replaced the parts using a soldering iron. I also thought that the lower lip and the check bow lines on the printed helmet weren't as defined as in the helmet from the movie. So I just add the line and volume where I think it's necessary. Also, the holes in the printed helmet turn out not as clean and large as they seemed on the virtual 3D model. Therefore, for each hole I turned brass inserts and soldered them into the part. Of course, you don't have to go all out, you can just carefully rim the holes or print such inserts on the 3D printer, but imagine how much easier it is to clean metal holes with a regular drill after numerous layers of primer. In short, don't be afraid to make changes to the master model even after 3D printing, if you think it's necessary. After making all the changes, we level the deep print defects and scars from the plastic surgery to change the shape of the cheeks and lips. Fill the recesses with 2K filler, and after it, we remove the excess filler with 180 grit sandpaper. When the deep defects are smoothed out, we move on to the standard smoothing workflow on the entire surface. Degrease and remove dust from the part, then apply a light, dusty coat of primer. When the dusty coat is dry, then generously flood the part with several layers of high-build leveling primer or filler. After that, apply another dusty coat of primer, preferably in a different contrasting color. This guide layer will make the smoothing process much convenient because you will see very clearly where the surface is already smooth and where more work is needed. Try to find a primer that has a good adhesion to plastic, provides a really thick layer for quality leveling, and doesn't clog sandpaper too much so we can blow it out and reuse it several times. After smoothing, the part is coated with a thin layer of spray paint. It's better to make a few test samples first and scratch them with a fingernail after they dry. It often happens that the spray paints of different colors from the same brand have completely different properties. Let's take a popular local brand Kuda for example. All metallic sprays have excellent adhesion and predictably hard surface after drying. But all the color sprays, especially red one, adhere much worse to the primer and are softer even after full drying than the metallic ones. After smoothing and painting, we need to turn the part into a master model for casting. If there are holes like the eyes, we seal them with clay and mount the helmet on a base. This base will later form the powering sprue of the mold, but you'll see it a bit later why it's really needed. The base also can be made with clay. During the whole workflow you'll need a lot of modeling clay to create a casting mold, and it's good that it can be reused. Simply melt the used pieces of clay in a pot until liquid, then pour it into DIY mold made of wooden sticks. When our homemade clay bar cools down, we get a neat block of clay of specified thickness, just like the brand new one from the shop, and it can be used again. Before working with silicone, it is essential to apply mold release wax to both the part itself and the plywood table. When trying new materials, always start by making test batches, test pours, and check the compatibility of all the components you plan to use together. On the Smooth & Company YouTube channel you will find a good detailed video tutorial on this technology, also using an Ironman helmet. If you decide to do it yourself, I highly recommend watching it, it's an excellent educational video. However, guys at Smooth On work with best supplies that are impossible to get there in my country right now, so I decided to show the entire process as well, but with materials I was able to find. Making a silicone mold takes about 12 hours, and this process cannot be split over several days. Therefore, before you start, make sure you have enough time to complete the work without rush. After applying the release agent, measure and mix the silicone with the pigment, then add the catalyst. If the mixture is too runny, add a little thickener. The first layer is the most important. It must capture every detail of the master model as accurately as possible. Therefore, apply it with a good new brush that doesn't shed bristles, using a stippling motion, ensuring the silicone fills all the details tightly without leaving any bubbles or uncovered spots. After the layer has dried to a tacky state, when it's still sticky but no longer comes off on your finger, apply the second layer, adding a pigment of a different color so you can see any missed spots. The goal of the second layer is to build up the thickness evenly. Apply the silicone with a brush, but now with smoothing motions. Again, if the silicone is too liquid, add thickener to it. Note that as the silicone nears its expiration date, it thickens, so whether to add thickener or not is best to decide right before application. Right after applying the second layer, you can make small silicone castings that will later act as locks, preventing the silicone from shifting inside the hard shell. You will need 5 small truncated cones, preferably with steeper walls angles than mine, because then they won't pop out of the shell, and a half-meter strip which can be cast in aluminum profile. The next layer I would call 2.5 because it's not applied to the entire area but only into the recesses and undercuts. At this time you can add more thickener so the silicone doesn't run at all and holds well in the recesses. This layer is easier to apply not with a brush but with a wooden spatula. To find it faster on Marketplace, search for sugaring spatula. Let the girl at the pickup point not think you're only interested in car parts and sports nutrition. Next, a full third layer. Make it the same color as layer 2.5. The task is to apply a layer evenly over the entire surface and smooth out the relief. Apply this layer with a brush using smoothing motions. Add thickener to the next 4 layer, not as much as in 2.5 when we fill the recesses, but enough so the silicone barely runs even on the vertical walls. This is because we now need to build the main thickness, which will provide sufficient rigidity for the mold. For this, the average thickness of the silicone mold should be about 5 mm. A mold that is too thin will tear, and ones that are too thick will be difficult to remove from castings. When our 4th layer has set, glue the already cured logs to it using silicone. We need to glue 6 rectangular logs to the silicone skirt and the cones onto the helmet, 1 to the very top point, on the ears, 1 to the front and 1 to the back. To prevent the keys from sliding, secure them additionally with pins. Once the silicone used to glue the keys has already cured, all that's left is to apply a final layer of silicone over the resulting pin head shape. The task is to reinforce the keys with a solid unifying layer and to smooth out any remaining imperfections as well as possible. Don't be lazy and correct any drips if necessary until this layer cures. The smoother it turns out, the fewer problems you'll have at the next stage. The process of making the silicone mold is complete, and now you can take a break before making the hard shell. After the silicone mold has completely dried, we cut off the uneven edge of the flange and mark the center line. Depending on the complexity of the master model, the hard shell always consists of several parts and is made to be separable. In our case, it will be sufficient to split it into the left and right halves, which will be fabricated separately. To do this, we built a clay wall directly along the center line, again using repeatedly recycled modeling clay for economy. To ensure the left and right parts of the shell always mate with each other in the exact same position, we add some kind of locks. Note the trap shape of locks walls. This is done specifically to make it easier to disassemble and reassemble the mold later. The wall must be rigid enough to hold its shape when several layers of fiberglass are laid over it. Therefore, besides using a sufficient thickness of clay, it's better to craft a kind of reinforcement from scrap materials on the side that won't be laminated yet. When doing the final shaping of the wall, it's better to smooth out any clay imperfections and slightly round all corners, especially the angles between the wall and the silicone. All these extra efforts will make the next lamination process simple and enjoyable. This is what the model looks like at this stage, ready for lamination. All that's left to do is to apply release agent to the table, the silicone and the clay wall. I also prefer to prepare the fiberglass cloth before lamination so I don't get scissors dirty while working with epoxy. Now we mix the epoxy resin, apply it to the work surface and begin lamination. Lay the cut fiberglass pieces with some overlaps and saturate them with resin using a brush and metal rollers. I showed how to make these DIY rollers in previous videos about composites. Wait a couple of hours for the first layer to harden and apply 2 more layers in the same manner. The shell won't be under extreme stress, so 3 layers of any structural fiberglass cloth with a density around 200 grams per square meter will work great. After the epoxy has fully cured, we disassemble the clay wall, sorting the clay into 5% that's unusable with some fiberglass in it and 95% that's perfectly usable, which can be melted again and reused. Now we densify and slightly round the angle between the wall and the silicone to prevent epoxy from leaking into this gap. After applying a release agent to the section, we repeat the lamination process on the other side. After the second half has fully cured, we move on to the dirtiest and most disliked stage. The cured edges of the fiberglass, soaked in epoxy, form thousands of tiny needles that will certainly try to get into your skin and lungs. Therefore, always use bath protection at this stage. Trim off all the rough edges and sand the entire remaining surface of the fiberglass. In all next stages we will have to constantly handle this form for long periods, so it's better to ensure no needles are sticking out. Also, while everything is already messy, we drill 4 holes in the wall through which the left and right halves will be bolted together. Carefully, using plastic pry bars to avoid damaging the silicone, we separate the mold into its 2 halves. Once the fiberglass is completely separated from the silicone, we can finish processing all the rough edges, clean up, and move on to the most exciting step.
Last time, for example, the silicone mold turned out to be too thin, but most critically, the extremely expensive release agent somehow didn't work at all, even though I did everything by the book. In the end, the silicone bonded permanently to the master model, and I couldn't even peel it off, at least to save the master model and not have to start from scratch. Only because of one faulty consumable, which, by the way, worked fine on the test samples but failed completely on the helmet, I ruined a month of work. This is why now I try to show in the frame the consumables that actually work.
To reduce the friction of the silicone when removing the mold, we dust it with baby powder and distribute it evenly over the surface. Now, very carefully and without rushing, we begin to separate the mold from the model. Important: do not try to remove the silicone in one motion, it's better to slowly pull it back and work with your hand inside. If everything works out, we inspect the silicone surface for defects. This is only my second mold, so I did miss a couple of bubbles in the first layer, but overall everything is great and we can proceed. So we assemble the mold, tighten it with bolts, and now everything is ready for the mass production of helmets. Most often for this kind of casting, a 2-component polyurethane plastic is used, which hardens quickly after the base and catalyst are mixed. First, thoroughly mix each component separately, stirring but not shaking, to get as few air bubbles as possible. Then mix the components in the specified proportions and immediately pour it into the mold. For all the time the plastic remains workable, we rotate the mold in different directions, trying to distribute plastic as evenly as possible over the entire surface. It's impossible to achieve the full thickness in a single pour because the weight of the plastic will then pull the silicone away from the mold. Therefore, after the first layer has slightly hardened but is still tacky, we pour the second layer. Repeat this as many times as needed to achieve the optimal balance of strength and weight. When rotocasting, be sure to consider that the lifetime specified in the technical datasheet, for example 8 minutes for replicast long plastic, is typically calculated for thick castings. In such castings, the plastic hardens much faster because the thicker the layer, the more the plastic heats up with exothermic reaction and the faster it cures. Therefore, for thin layer castings like ours, the lifetime can extend to 20 or 30 minutes, and it is better to continue distributing plastic throughout this entire time. A couple of hours after pouring the last layer, even without waiting for the final cure, the helmet can be removed from the mold and you can start making the second one, while the first one gains its final strength. Thus, if desired, in one working day you can make 3 or even 4 helmets with strength comparable to those 3D printed. Just imagine, to print and manually smooth one such helmet, you need at least 4 full working days. With casting, you can get 3 or 4 helmets in one day. If I only wanted to sell helmets on Etsy, I would have stopped at this stage. But we are sticking to the plan, which means these castings need to be reinforced.
According to the original plan, all I had left to do with the helmet after casting was to reinforce it with composite materials. One day of work, I thought. But it turned out that our wonderful plastic has absolutely no adhesion to an epoxy resin. Of course, I tried sanding, dusting, degreasing, using adhesion promoters and very possible combination of primers. Nothing helped. To help you truly understand the depth of my despair, I even tried replacing the casting plastic with polyester gel coat and making a lamination with polyester resin. But this time the neighbors couldn't take it. Anyone who has ever worked with polyester knows what I'm talking about. When a small jar of polyester arrives at the pickup point on the next street, you know that not from the app, you just smell through the entire neighborhood. I'm really amazed by polyester ability to sting so hard even through the glass. And I would have been ready to do casting in an open field, but the problem is also that polyester gel coat turned out to have very weak adhesion to the silicone mold, which again was not an option. In short, I hit a wall. I couldn't reinforce the casting with composite, meaning I couldn't do the very thing this all work was all about. You might say, Alex, couldn't you have, before all this long work, made small test samples of the plastic and tried to glue a piece of fiberglass cloth to them? And I'll tell you, I did exactly that, and everything glued perfectly. But any technologist will tell you that not everything that works on the test samples works on final parts. In this case, with small test samples, a critical factor was missing: the time interval required for applying the resin and laminating. With test samples, it's a few seconds. With large castings, it's nearly 1 hour and more. I was tempted to make a huge dramatic 2 hours long video to show you all my struggles, especially since I wasn't even sure if anything would work out in the end, because I couldn't find any single video or article where someone successfully bonded casting plastic with epoxy. But persistence overcomes resistance. In short, after numerous failed laminations, I noted that every type of casting plastic has its own very short polymerization phase, measured not even in minutes but in seconds, when it has thickened enough not to pull away from the previous layer or stick too much to the brush, but at the same time it remains plastic enough that if epoxy applied at this exact moment, it mixes with the epoxy on chemical level and creates adhesion that wouldn't happen a moment later or moment earlier. So the solution was to wait for this precise polymerization moment and within at most 1 minute apply the epoxy to the plastic, and that's it. Applause. And once the solution was found, I made as many helmets from fiberglass, carbon fiber and Kevlar as I had supplies for. Of course, I would tell you exactly when this phase occurs, but it depends on a huge amount of factors. So the most accurate thing I can say is that for replicas long casting plastic at 25 degrees centigrade, 50% humidity and a mixed volume of 180 milliliters, this phase occurs at 6.5 minutes. So to get it, you need experiment right during the casting, but the key thing, there is a solution.
Now, after 2 months of struggling with adhesion, I could finally continue with the original plan and move on to composite reinforcement. Pay attention that laminating and inner walls with such detailed surface is much more challenging than just laying large sheets of fiberglass on big flat surfaces. So I want to share some tips on how to do it best. Just note, during video editing I used footages from a dozen different helmets, so don't be confused if the epoxy color or composite materials vary between neighbor shots. Since the lamination needs to be done quickly, it's better to pre-cut the required fabric. Take fiberglass, carbon fiber, Kevlar or my favorite, carbon Kevlar twill, unroll it and mark 10 cm from the edge. Now pull out a bundle of threads opposite our mark and you get visible cutting line. Thanks to this way, the cut lines will always run parallel to the weave and the cutting pattern won't drift. We also cut the resulting strips into 10 cm segments, getting 10 cm squares. These squares are suitable for laminating areas without fine details like the back of the head or the helmet side walls. And if you cut these squares in half and then in half again, you quickly get pieces for laminating smaller details. But for the smallest undercuts and corners, it's best to buy or cut yourself narrow strips from fiberglass or carbon fiber. So, if we manage to correctly catch the polymerization phase of the plastic and quickly apply epoxy resin to it, we have about 1 hour to lay up the first composite layer. For the first layer, it's better to use a material with low density because thin fabrics wrap more easily and conform better to complex relief than high-density fabrics. If you're reinforcing with fiberglass, twill with a density of 160 grams per square meters is the best option. For a carbon fiber helmet, use also twill with a density up to 200 grams per square meter. For a Kevlar helmet, it's best to use carbon Kevlar twill with a density up to 200 grams per square meter. Pure Kevlar lays up too stubbornly, especially at the first layer. Right after mixing, while the epoxy is still runny, it's easier to quickly place and saturate large pieces. Once the main area is covered and the epoxy has thickened slightly, we place fiberglass or carbon fiber strips into the steepest corners and undercuts, trying to make the lamination as dense as possible. Note that when laminating 3D printed parts, you don't need to obsess as much about packing undercuts, because even 2 or 3 layers of plastic have decent strength and small delaminations between plastic and composite aren't so critical. In our case, however, the thickness of the outer layer formed by the casting plastic is usually less than 1 mm. If the composite doesn't adhere to it tightly, an air bubble will form between the plastic and the composite, and as a result, the plastic in that spot could be easily pressed in even with a finger. Within the first couple of hours after epoxy mix, before the resin has fully set, it's better to adjust the layer and sometimes compress it if you see that in some places the fiberglass is starting to pull away from the plastic. After a couple of hours of curing, next layers can be applied using the material you've chosen. Fiberglass and carbon fiber will laminate more easily. Kevlar is a bit trickier, but overall, if the first layer is of good quality, all the next layers laminate without problems. When starting a new layer while the resin is still liquid, first cover large flat areas using large pieces of fabric. And when the epoxy starts to thicken, that's actually convenient for laminating areas with high detail like face and ears. These are best done with small pieces. In the same way, we build up the necessary numbers of layers. Once sure that the final layer, even after a couple of hours of curing, no longer needs adjustments, we can take a break. After the resin has fully cured, we disassemble the shell, remove the finished parts from the silicone mold and go on with post-processing. First, we trim off the excess material. The only 2 reasons I'm not wearing full protective suit in these shots that are it was 30 degrees Celsius in garage this summer, and second, when you cut tightly laminated fiberglass, it only breaks into crumbs, not needles. But in any case, safety glasses, a respirator gloves, long sleeves and a powerful air hood are absolutely essential. After trimming the excesses, we proceed to craniotomy. Where possible, we use a Dremel. Where the Dremel cannot reach, we perforate the cut line with 1 mm drill bit to make hand cutting easier, then use a metal saw blade or a handheld jigsaw. In the later models, once I got the hang of achieving a dense laminate even in complex corners and recesses, this problem didn't occur anymore. But in the early versions, after cutting, it was noticeable that the lamination hadn't settled properly in the corners. Such issues are fixed using a DIY UV curing putty. We take resin for SLA printing and add some baby powder to it until a thick paste forms. Apply this putty to one section, cure it for a few seconds with a UV flashlight so the putty hardens slightly and doesn't stain. Then move on to the next section. Once the entire putty is filled, give it a final cure in a UV chamber, or if you don't have one, simply leave it in the sunlight so the resin fully hardens. Then we sand off any excess putty. In terms of hardness, this putty is much closer to the casting plastic than 2 soft acrylic 1-component putties or 2 hard polyester 2-component putties. This makes it much easier to smooth and, most importantly, easier to work with, because you decide when it needs to harden.
Further surface processing can be different depending on what kind of coating you want to apply. From elementary spray painting to electroplated metal coating, but the topic of various coating I think is covered quite well in the Basics of Composite playlist. To sum up, what does this technology give us? We continue to enjoy all the benefits of 3D printing using cheaper printers without heated chamber and all the benefits of PLA plastic. But the final part doesn't contain PLA plastic at all and none of its operational flaws. At the same time, the part's surface layer is already smooth, ready for painting, and the weight to strength ratio of the body can be almost anything. Once the casting mold is made, it can be used to produce parts that looks identical on the outside but can be absolutely different in purpose and strength. For example, we can cast just one layer of plastic to form the detailed surface layer and reinforce it with any composite material. This way, we get a helmet that looks like the original one from the movie and offers protective properties similar to a motorcycle helmet. At the same time, using the same ready-made mold, we can make castings with 3-4 layers of plastic to quickly produce lightweight versions of this helmet that visually look the same. These versions are suitable for cosplay and small-scale production, which helps compensate at least some of the high costs of creating the master model and the mold. High costs are indeed downside of this technology. As you can see, the production cycle is truly long and expensive, so if you only need one part, you would likely choose another manufacturing method. Other nuances. The nature of casting itself is such that the final part essentially absorbs all the flaws from the previous stage, and since there are many stages, there can be quite a few flaws. If there is a scratch on the master model, it will be on the final casting. If any air bubble gets trapped in the silicone, casting plastic will fill it, creating minor but visible defects. If the silicone was too liquid or too dense, the mold will be too thin or too thick. If both silicone and plastic seem suitable, but they are slightly expired, thickened or absorbed moisture from air, the result will be defective. If at any stage the release agent fails, the result will be defective. In short, this technology is indeed quite complex and very sensitive to the quality of consumables. After all, it's the same as with any other production technology, there are some pros and cons. But now that you've seen all the entire process visually, you can decide for yourself if this way suits you or not. At this stage, this technology is good for me because with combination of casting and composite reinforcement, I can finally make body parts with my own hands that have the properties I could never achieve before. Now, what's next on our plan? To maintain a logical storyline, I want to release a comprehensive overview video on composites very soon. It will summarize all my research in this area for the last 4 years, plus I will show you something new. After the composite video, with a sense of accomplishment, I'll be able to post updates about the internal components of the suit. The entire step-by-step building instructions of Ironman reactor and basic model of repulsor and exosuit, high pressure and high power electrolyzer drawings are available for Alex Lab channel members and Patreon members. Guys, thank you so much for the opportunity to do what I do. Also, subscribe to my Instagram if you want to follow the day-to-day life of my workshop and sometimes see content that YouTube doesn't allow me. Click the like, share this video with your friend, and of course don't forget to become Alex Lab members to get access to all my books, technical drawings and 3D models. Good luck with your own projects, see you soon!